I want to solve for you WebAssign problem number 9 of the magnetic forces on currents. It's not an A, it's a 9. And it has to do with the net force on the coil of a loudspeaker with the magnetic field configuration specified for you. So basically, we have this coil, all right, and it's got 50 turns. N is equal to 50. That's going to be important because each turn contributes equally to forces and magnetic fields for that matter as well. Now, from an axis through this thing, with respect to that 60 degrees, we have a B field. So I'm going to transpose this axis over here. There's a B field, magnetic field, at 60 degrees from this direction. So I'm going to draw it like this. There's a 60-degree angle, and that's the direction of the magnetic field. All right. And the current, I'll draw the current flowing like this. The current is flowing around the loop as shown in your picture, a little better than this one. But in any case, as the current goes around there, this magnetic field is in the direction that I show here everywhere around the loop. You know, over here it's up like this, etc. So when the current goes over here, I'm going to draw this as the current going into the page. There's an X. That's kind of hard to see, but you can hear me. That's current. And there's a magnetic field. Now, the fundamental equation is magnetic force is equal to ILB sine of theta. Theta being the angle between I and B. But if I's going in like this, whoops, can't see that very well. I's going into the page, and this is off in this direction. What you got to realize is no matter what direction this B is, as long as it's perpendicular to the I, and it is, it's actually perpendicular. You got a wire, and there's a B field in some radial direction going off. This is like a radial direction coming off that current, radially off that current line. And that's important. Turn that light off and on. I guess the lighting's good. So really, this sine of theta, the direction between I and B is 90 degrees. So this is ILB, all right? Now, the formula is really better written as this. Because each wire contributes this. There's really 50 wires. The coil has 50 turns. So it's really NILB. That's the magnetic force on the coil. There it is. But what is the direction of that force? Well, the direction of the force is perpendicular. And if you do the right-hand rule, you discover really it's perpendicular to the motion of the charges, which is in, and perpendicular to the B field. And that solution is like this. So this is the FB. This is the magnetic force. And this is 30 degrees based on the conditions given. So that force, 30 degrees, directed away from, a line that's in the direction of motion of the coil and magnet, to drive the loudspeaker. The net force, F net, is really FB, the amount of this. Here, let me draw it out here. We have, right now, we have the magnetic force, but really, if you add all these forces around the entire loop, they're not all in the same direction, obviously. The X components will cancel as you go around the entire loop, and you're left with, I'll say, FB parallel, the parallel part of it. Since this is 30 degrees, it's really the parallel part of this FB. Therefore, F net is equal to the total magnetic force. I'm going to say cosine of 30 degrees, or you could say sine of 60 degrees. And that would be the sine of this 60-degree angle would be the same amount. So that's going to be the F net. Basically, it's F parallel. Okay, so with all that clarification, and I think it's important, clarification is needed, we can conclude, is that thing focused? Doot, doot. All right, I guess it's good enough. We can conclude that the net force is, all right, I should probably clarify up here, FB cosine of theta is NILB cosine of theta. That's really your answer. I could probably stop at that point. Let me just take it a little bit further. This is going to be the stuff that's given. For everybody has the same N, which is 50. Different I. The L is the length of the wire is the circumference, which is pi times the diameter. People have a different diameter, right? And then B field. Okay, so I'm writing everything. I'll go ahead and put the I in here, and the B cosine of theta. So this is then equal to 50 pi, everybody has that, cosine of 30 degrees, everybody had that same thing, and multiplied by the variables for each person, which was the current, the diameter, and the B field. So that's going to be equal to 136 IdB. Now, my particular example, I had the current was 0.85 amps. The diameter was 1.55 centimeters. That's 0.0155 meters, of course. And the B field was 0.28, and that is equal to 0.502 newtons for my particular example. So that is how you solve that problem. You don't want to use any torque equation because there is no torque on this current loop based on what's going on, based on the symmetry of the situation. There you go.